먼저 영국의 핀테크 기업인 오피텍의 창업자이자 CEO이신 varqa Abyaneh 박사님께서 금융시장에서의 양자기술 잠재력 탐구라는 주제로 강연을 하시겠습니다. 여러분 뜨거운 박수로 맞이해 주시기 바랍니다.
Hello there, my name is Varqa Abyaneh, I'm founder and CEO of Opitech. I'm here to talk to you today about exploring quantum potential in financial markets. So what I'm going to cover are a number of topics in finance. The first is counterparty risk, and that's basically quantum use cases to do with counterparty risk. So we're going to cover what is counterparty risk, what is the concept called default and contagion, how optimization can be a solution to this, and what is a form of the optimization objective function, and what are the quantum applications therein. Then we're going to talk about asset allocation, quantum use cases there, and we're going to talk in particular, we're going to introduce what is asset allocation, and then talk about the quantum potential. After that, we're going to talk about CVA and Monte Carlo. So CVA is known as credit valuation adjustment, what are its quantum use cases, and then we're going to jump into products that we're working on at Opitech. So the first is something called counterparty selection, and in order to explain that, I first need to tell you what a request for quote is, a request for quote trading that is, and then we're going to talk about, after that we're going to talk about another product called RES Trader Assistant, which is an AI, and what is the quantum potential there. So two products that we're working on at Opitech. And then finally, if time is permitting, we're going to talk to you about some research and development that's nothing to do with finance, but to do with purely quantum mechanics. Right, so let's start with counterparty risk. So what is counterparty risk? To understand counterparty risk, I'm going to first need to tell you what market risk is. Market risk is a total risk that a certain party has against all counterparties. Counterparty risk is the risk at a party and counterparty level. Let's make this explicit. Let's say I've got two parties, and I'm going to try and use a laser pointer now. Let's see if this works. Okay. Yeah, so I've got over here, party A has got some Apple stock risk, and it's got risk against counterparty 1, counterparty 2, and counterparty 3. It's got $10 it's bought from counterparty 1, and it's got no risk against counterparty 2 and 3. The total Apple stock risk that the party A has is $10. Now, let's look at party B's risk. Party B has got risk, $20 it's bought from counterparty 1, it's bought $5 from counterparty 2, and it's sold $15 to counterparty 3. The total risk over here is again $10. Both of these parties have got the same market risk, but they've got different counterparty risk. Party B actually has got more counterparty risk than counterparty A. So now let's jump into looking at default and contagion, and I'm going to talk a bit about the financial ecosystem. So the large banks, of which we've got representation over here, they're called dealer banks. That's JPM, HSBC, Morgan Stanley, Credit Suisse. All of these banks trade with one another. They all have got risk against each other. Then there's a universe of clients. Who are the clients? Asset managers, pension funds, hedge funds, corporates. All of these have got risk against each of these large banks because the banks service these clients. Then you've got clearinghouses. Clearinghouses and exchanges are central nodes which act as a central counterparty for all trades. And guess what? Every single one of these institutions, the dealer banks and the clients, have got risk against clearinghouses. What does this mean? There is an interconnected risk web. It's complex, it spans multiple assets, not just Apple stock, but we're talking every single derivative contract, every single stock, bond, complex exotic structures, all of that across multiple entities. There's a contagion effect. Contagion is the effect of a default of a single party has on the rest of the financial ecosystem. So let's imagine that one of these dealer banks is to go bankrupt. We do not know what the resulting impact of that bankruptcy is on the rest of the financial system. This was a huge problem in 2008, in the Lehman crisis. The financial system did not know who to rescue, which banks should you bail out and which should you let default, for fear of the contagion effect on the rest of the financial ecosystem. So what happened is strict regulations were put in place. Banks and clients now have to hold margin and capital against their counterparty risk positions. And that's very good, because since 2008, well, in fact, the rules came into effect around 2016 or 17. Since those rules came into effect, the regulators can feel more happy to let certain counterparties default because they know they have this capital and margin buffer. But the business cost, the impact, is material. It is now more expensive to do business between financial institutions because they have to hold capital and margin reserves. So we've covered counterparty risk, we've covered default and contagion. Now let's talk about where optimization is a solution. Now this was a product I was involved in launching at a previous company which was exited to the London Stock Exchange. So the optimization solution that we launched and is now live across all of the large banks and the large majority of the hedge funds is every single party submits their counterparty risk to a central vendor. That vendor does an optimization and it proposes a set of trades that reduces the counterparty risk but maintains the market risk position. So in the previous role I was a derivatives trader. I cared about what my total risk was, my market risk. I didn't care about what my counterparty risk was. That was the job of someone else, the CVA trader. We now outsource that to a central vendor. The central vendor produces a set of trades that's market risk flat and reduces counterparty risk. Once that proposal is done, all the banks sign off, and once they all sign off, all the trades are executed in one go, and margin and capital reduction the margin and capital requirements are reduced, and there's less counterparty risk. Let's give an explicit example. We've got over here some initial Apple stock risk again, where the parties got risk against counterparty 1, 2, and 3. They bought 20 from counterparty 1, bought 5 from counterparty 2, and sold 15 from counterparty 3. The total is 10. The optimization trades that might be given from an optimization would say sell 10 to counterparty 1, sell 5 to counterparty 2, and buy 15 from counterparty 3. You see, it's changing the counterparty, but if you add them all together, the total risk change is 0. That's a constraint of the optimization. And the result is something that looks much more neater. The party has only got risk now against counterparty 1, and if you look, its counterparty risk is $10 against counterparty 1, and its total risk is $10. That is much more optimized. Okay, now that was a very simple example of reducing counterparty risk. Really, these formulations of margin and capital requirements are more complex, and the optimization is far more complex and involves correlations and models. However, we can talk about the structure of the objective function, and it's generally built up of something called a linear term, a convex term, it's got a non-convex term, and it's got a combinatorial term. So the linear term is easy to optimize. Why? And I'm not going to go into too much detail over here, but a linear term typically looks like a straight, flat sheet of paper in high dimensional space, and it's very easy to find the minimum. So imagine if you look at this slope over here, this is what the linear term looks like. It's very easy to find the bottom of this just by sliding down the slide. The convex term is also simple. It's a little bit more complex than the linear term, but it's very easy to optimize. If I want to find where is the minimum of this bowl, wherever I start off, it's very easy for me to find the mathematical minimum. The non-convex term, though, has got multiple minima. This is computationally harder to solve. You can find the minimum of each of these values, but you still need to try each of these values. A combinatorial term is even harder. This is where the only way you can find out what the best solution is to do every single one of the permutations individually. There is no neat trick you can do other than brute force computation. So where's quantum computing going to be useful? It's in these last two terms. It's these types of optimizations over here. Okay? These are simple, they can be done normally. However, these two can get more complex. So that's the first use case, counterparty optimization. Now let's talk about asset allocation. So what is asset allocation? You've got portfolio, we'll start off with portfolio optimization. So if you're an asset manager, you have typically a bunch of portfolio managers. They sit there and they decide what assets to invest in. What they do is they do an optimization either in their head or using a computer, or both, where they decide that they want to maximize the return while minimizing the risk. The key constraints that they have on the optimization is that they want to maybe have certain restrictions on what they're allowed to trade. They might have a constraint on something called value at risk, which is a certain function of the trades that they've got. They might have ESG, environmental sustainability and growth requirements, and they might have liquidity needs. So these form the constraints. So what they're trying to optimize for is maximizing the returns and minimizing the risk. But what they want to constrain for is number two. The traditional approach uses standard models. Now, standard models imply that this optimization can become convex. And as we talked before, convex optimizations are easy. However, that's a limitation due to computational resource. If we were to use a more complex and real-world objective function, we could get a much better portfolio. But that would come with a computational cost, and that's why quantum computing could be useful. And I'll jump into a bit more detail over here now. So the traditional approach, as we discussed before, it assumes what is called a simple probability distribution function, and that's to keep the objective function convex. We could use machine learning and basically give our probability distribution. So let me be clear on this. By this I mean the probability distribution is what does my future probability distribution look like for every single possible asset I can invest in. That might have many, many parameters. And actually we don't know how many parameters they've got. We could give a machine learning engine a whole bunch of parameters to play with. In fact, that machine learning engine might even find patterns that we humans yet haven't recognized. It would become more complex, more accurate, would require more compute power. But that's where quantum machine learning can come in to help on the training aspect of it. Furthermore, the resulting objective function itself might no longer be convex. And as we discussed before, non-convex optimizations are complex and could require quantum computing. So over here, you've got a dual quantum advantage. You've got one on the actual machine learning to calibrate the probability distribution itself, and then what you've also got is one on the objective function, or the optimization. Okay, we've covered two of the use cases. Now let's move on to the third one, CVA and Monte Carlo. So CVA stands for Credit Valuation Adjustment. When two banks or two clients want to trade a derivative with one another, there is a fair mid-market value for that. The credit valuation adjustment is what adjustment do I make for that price based on the counterparty that I'm trading with, which is a function of what risk I have against that counterparty. So for example, if I do a trade against a counterparty who I think is not going to pay me back, I'm going to charge a premium on top of that trade, and that's called the CVA adjustment. The formulation looks something like this. It basically says that between naught and capital T, which is the longest trade that I have with that counterparty, I've got an expected exposure. How much money do I expect that they're going to owe me at time T? Then I multiply that by what do I think is a chance that they're going to default and not pay me back. And by the way, that can be inferred from the credit default swap market. And then finally, I say, how much of that loss do I think I'm going to recoup? Now, the important thing over here is that expected exposure is an expectation calculation and requires Monte Carlo. However, the integral itself requires you to do one of these Monte Carlo calculations for every single time. So what you have is you have this situation where you're trying to use a Monte Carlo, and for those, I apologise if anyone here doesn't know what Monte Carlo is, but Monte Carlo is a calculation that involves calculating many branches simultaneously and taking the average value of those branches. You end up with this nested Monte Carlo situation. That's a computational challenge, and these CVA calculations can take a very, very long time. Now, without going into detail, quantum amplitude estimation offers a quadratic speed-up to Monte Carlo. So this could be a big game changer in how you calculate CVA, credit valuation adjustments. Okay, so we've now covered the existing products. Now let's talk about what Opitec are working on and quantum use cases here. So before I talk about the Opitec product, I need to give a bit of background about the markets and tell you what is a request to quote. So request to quote is if you have got a buyer and they want to go and trade something, and that product that they want to trade is not listed on an exchange, which means they cannot see the price of that product, they have to call up another bank or go via a salesperson to speak to another bank to get a price on that. So the traditional process is a bank calls up another bank or goes via a human broker. For example, when I was a trader, we would have brokers who would sit between us and another bank, and they would literally be doing this, matching my requests with the counterparty asking for a price. That definition is a request for quote trading called RFQ. What's interesting is it accounts for 40% of all market transactions. That's 1,400 trillion a year out of 3,400 trillion a year of exchange contracts. That process of matching buyers with sellers, when you don't know what price the seller is going to give, is a problem. Because how do you know which person to ask if you don't know what price they're going to give? You want to ask the best person. So the existing solution is something that looks literally like this picture over here. It's a broker holding two phones, negotiating. And believe it or not, this still goes on today in the market. Buyers find sellers by calling them direct or using an intermediary or a salesperson or a broker. So the buyer asks the broker, or they go via a salesperson, or they call up the counterparty direct. In all cases, it's purely based on relationship, or what the buyer's perception is of the seller's institution. So I know 10 traders at 3 banks, and I think I'm going to ask those 3 because I hope that they're going to give me the best price. These brokers and sales are very expensive to hire. They can only manage a finite number of clients. They cannot efficiently interpret data, and they cannot guarantee best execution as a result. And best execution is a regulatory requirement. So Opitec's solution is we have something called counterparty selector. So we're using a machine learning neural network to match the buyers with sellers. So rather than going via a salesperson, you go via ARIS, counterparty selector. And ARIS says, well, I know all the traders at all the banks, and I'm using machine learning and AI to find the best seller. A little bit more detail on how this works is counterparty selector takes in all client pricing data, so banks can connect to us direct and give us their data, vendor type pricing data, so any data from exchange or any brokerage or any dealer platform we can absorb, and any available market data. And then we have got a machine learning neural network that's calibrated to that to then rank which counterparties you should go to, given the trade that you're asking for, asking the size that you're asking, the time of day that you're asking, all of these things. The quantum benefit over here is that this machine learning, as we've discussed before, can itself become a quantum process. Okay? If the optimization becomes complex or mixed integer, we're going to get an advantage. But also, as this machine learning gets more complex, we give it more parameterization, it will get better and better, and there might be quantum applications over there. Our next product is ARIS Trader Assistant. So we have built an AI that revolutionizes workflows by assisting traders with complex analysis and optimizing decision-making process. So we've trained the AI to think like a trader, and it can propose RFQ. You now know what an RFQ is, trading strategies. It can propose that to the trader on how best to reduce the trader's risk. We've also trained it to think like a quant, so it can understand and interpret and call traditional pricing libraries for derivatives. Given that it's a trader, it also knows how to sell, because selling and trading are the same thing. In both cases, the salesperson is helping someone else to make money, and the trader themselves are trying to manage risk. And then finally, given that it's an LLM, it can also negotiate and broker trades, which is a job currently done by humans. So that's a product. It provides AI-powered decision support, and we've taken a new way of doing this. Well, it used to be new, I think it's less new now, is rather than taking the standard API approach, where you use a large language model to do the following. The large language model helps call a set of predefined decision functions. And really, in the traditional approach, what you're doing is you're saying, I am using human language to call computer code. What we've done is we've basically taught the concepts to the AI itself. Now, the advantage over there is, in our process, is we don't have a set of predefined decision functions in the black box. Our AI, it writes a code and executes the code in real time, and it understands the concept. So it's not bound by a set of predefined functions, but it understands concepts. However, this takes a long time. It takes a long time to calibrate, it involves fine-tuning. It's also very complex and time-consuming to execute. So there's two potential quantum use cases here. One is fine-tuning and the training of the models itself. And the other one is, as I said before, our AI can write code and execute it in real time. So is there an opportunity that rather than writing Python code and executing it in real time, it could write quantum code and send it to a quantum computer and execute it in real time? Okay, so that concludes what we've been doing on the applications of finance, applications of quantum computing to finance. Just to end a little bit over here, I'm going to talk a little bit about some research and development that we're doing. This doesn't really have anything to do with finance, but is a little bit orthogonal. But what we're looking to do is we're doing theoretical work on a quantum Zeno-based ion trap. So what we have is we've tried to develop a novel way of trapping ions. Now, the traditional way of trapping ions, and before I go into this, ion traps are a strong candidate for qubits, right? So the quantum bit can be a trapped ion. The issue is when you trap an ion currently, you trap it with something called a Paul trap. So the ion that you have, you trap it using an electromagnetic field. Now, that's very good, and it works very well, and Paul got the Nobel Prize for it. However, the interaction between the ion and the electromagnetic field can cause the ion to lose its coherence. What does losing coherence mean? Well, losing coherence or decoherence is a process in which quantum mechanics becomes classical mechanics. And once a quantum system is decohered, it no longer has its quantum properties, and therefore it's no longer useful as a quantum bit. These electromagnetic fields can cause decoherence. So what we're looking to do is we're investigating a measurement-based approach. So this is rather than trapping the ion using an electromagnetic field, we're looking to do measurements on something else that's interacting with the ion, and therefore the ion can have potentially a much stronger coherence time. So in quantum Zeno effect, the idea of this is when you perform a measurement, a quantum measurement on a system, you change the state of the system, we have a paper out and it's a theoretical way of trapping an ion purely using measurements, therefore it doesn't have any electromagnetic field interaction, potentially can give much better coherence times. Now, why is a longer coherence time useful? It basically means that you can do better calculations on your quantum computer. What's the financial applications of that? Well, it's no different to any other application. A better quantum computer means a better tool for doing financial calculations. And I'm going to admit over here that I think I've still got a couple of minutes left, but I think that brings us to the end of the talk.
varqa 아브나야 박사님 강연 잘 들었습니다. 지금부터 질의응답 시간을 갖도록 하겠습니다. 질문이 있으신 분들은 자리에서 손을 들고 계시면 저희가 마이크를 전달해 드리도록 하겠습니다. 네, 김재원 의장님.
So it seems to me that you are providing financial solution and also this computational solution. So you are developing the quantum computer using quantum Zener effect.
So this is far more in its infantile research stage at the moment. So the products that we have built and the products that we're taking to market are finance and fintech based. So that's where we are primarily.
I'm sorry, can you say it again? I'm sorry about that.
Yeah, so we're primarily a fintech firm. So what we are doing is we are providing financial services and using the products that we talked about, Counterparty Selector and the RES Trader Assistant, the AI machine learning to recommend counterparties, and the AI to interact with traders. That's our primary products. This is much more in its infantile research stage.
저희는 아무래도 핀테크 회사이다 보니까 금융 서비스에 좀 집중을 하고 있습니다. 그래서 거래 상대방 위험을 측정하거나 혹은 아리어스와 같은 저희 트레이더 어시스턴트, 머신러닝을 활용해서 거래 상대방을 선정하는 이러한 곳에 집중을 하고 있고요. 말씀드렸던 연구 같은 경우에는 아직까지 초기 단계라고 보시면 되겠습니다.
네, 다음 질문으로 넘어가도록 하겠습니다.
My name is Daeung. I'm here. My name is Daeung and I'm from Samsung Global Research. I'm kind of new this field, so I don't have much knowledge in quantum computing. And it's a wonderful presentation. First, I had a chance to know about many things about quantum computing finance, but some question occurs to me. Which one is the first one is if I think the information asymmetry is kind of a business model for banks. I mean, like Goldman Sachs trading house, JP Morgan trading house, they have their information and they have their counterparties, and that kind of information is their business model. So if someone wants to buy some stock, and if someone want to sell their stock, and matching those kind of counterparty is kind of business model for their trading houses. But if they accept those kind of quantum computing, then I think it ruins their business models. So what are the advantages about accepting those kind of technology for their houses? What do you think?
Firstly, it's a very astute point, a very brilliant point, and part of long debates that we have with many of the banks. So as a general rule, any type of democratization play immediately can go against those who have got the largest amount of information. So let's even forget quantum computing. Let's talk about the time when exchanges were just a bunch of people in the pit trading with each other. The way that worked is you had people on the floor of the trading pit, and they gave each other good prices, and everyone else who wanted to come and trade with them got a worse price. And those in the pit made a lot of money, and everyone else didn't. However, democratization, and as technology grows, has always come to make everything more even. And the banks know this. In fact, as you know over here, some of the speakers are representing quantum computing from the banks. So the banks know that democratization is the right thing to do. There are regulatory pressures to make sure, in fact, best execution, finding the optimal counterparty, is a regulatory requirement. So there's not a question if we don't want to do it. Even if the banks don't want to do it, there's a regulatory requirement for them to ensure that everyone gets the best price. So we have this discussion all the time. However, as a general rule, the more you democratize, the less the trading costs become. So whilst your margin on each trade might fall, because before HSBC and Goldman's were only competing with JPM and Citi, but now they're competing with a much larger ecosystem. what happens is the amount of volume and trading increases, and you'll get more and more trading coming from smaller and smaller firms and from other developing countries, and that increase in volume will counteract the decrease in margins.
Okay, thank you. And there's another question.
잠시
잠시
통역을 하도록 하겠습니다. 네, 먼저 질문 주신 질문에 대해서 좀 간략하게 요약을 해서 말씀을 드리면 지금 이 골드만삭스라든지 JP모건 같은 이러한 거래소에서 거래 상대방을 선정하는 것은 그 할 때의 정보가 그 비즈니스 모델, 그러니까 그 각 회사의 비즈니스 모델에 녹아있는 정보일 텐데 이를 받아들이는 회사들이 왜 이 기술에 어떠한 이점이 있어서 받아들이느냐에 대한 질문을 하셨는데요. 이 답변을 좀 요약을 해서 말씀을 드리면 모든 기술이 이제 이 과거에 이 거래소를 생각을 해봤을 때 좋은 가격을 가지고 있는 사람과 아닌 사람에 대한 정보의 격차가 있었다면 지금 같은 경우에 기술이 더 많이 활용될수록 사실상 비용이 더 절감됩니다. 그리고 지금 큰 HSBC라든지 JP모건 이전에 서로가 이 경쟁을 했다면 지금은 더 큰 생태계 내에서 거래 상대방을 선정하고 그리고 증거금이라든지 여러 가지 요구 사항들을 맞추고 있는데요. 전체 거래가 상승할수록 실질적으로 이 증거금이라든지 비용 측면에서는 더 감소가 되게 됩니다. 그리고 거래 상대방을 선정하는 것 자체는 사실상 규제로도 선정을 해야 됩니다. 규제적으로 거래 상대방을 최적화된 거래 상대방을 선정해야 한다는 것이 규제적인 요구 사항이기 때문에 모두가 이 최적의 가격으로 이 거래 상대방을 선정할 수 있어야 된다라는 것이 현재의 규제이기 때문에 그 기술을 받아들일 수밖에 없지 않을까라고 이야기하셨습니다.
네, 시간 관계상 질의 응답을 마치도록 하겠습니다.